Hi, good morning. I'm Oliver Gao. I'm the director of Cornell System Engineering Program. I have been very fortunate to conduct what I call these system conversations with our international leaders that we bring to Cornell to give this Ezra System Seminar Series. So today I'm very delighted to have Professor Eleonora Riva Sanseverino. Eleonora, actually, she is a full professor in power system engineering at the University of Palermo since 2019. So she's actually the delegate of the rector of the University of Palermo for European Programs Coordination. In 2020, she has been nominated by the Italian Ministry of University and Research National as expert in Class 5 of Horizon Europe on climate, energy, and mobility. And she's also a national representative of the Driving Urban Transition Partnership. So because all these topics are very important, critical challenges that not only Italy, but I feel all the nations, all the world is facing. So Eleonora, it's a great pleasure to have you here. Welcome to Cornell. I'm sorry to hear the delays, the flight, but now you're here. We're very excited. So Eleonora, I was looking at not only your bio, but also I was looking at your website. I have been really amazed by the work you have done. I know that you are a professor in electrical engineering, but apparently the work you're doing is way beyond electrical engineering. I think not only me, and I believe our audience who will be watching this, we want to know more about you. Please share with us, how your work evolved and how from your, I believe, when we graduated with our PhD, we were trained to be very narrow, but now you're dealing with all these, these kind of urban transitions, this challenge. Tell us more about you.
Okay, thank you very much for the invitation, Oliver. It is my pleasure to be here and to get to know this systems program, which is very, very interesting. And I feel it's really very close to my current interest. And current interest really come from a long journey, which started in my high school. I come from classical studies, so I studied Latin and Greek, and then also literature. And after that, I started engineering studies, electrical engineering studies. But then I've been, as I mentioned before, I've been very much interested and conquered by other fields of the engineering and computer science, for example. So my PhD was in genetic algorithms for operational problems in power distribution systems. And so I've been also in the US during my PhD at Washington State University on the other side of the coast of the US. And but I mean, I've always been very curious. The point is that in the early career of researchers, you're very much focused on your technical topics and very much looking at the results of your research and going on and going ahead and innovating all the time. Now that I am a full professor, I really go back to my high school studies and I met again humans, which is really fascinating. So the interface between technology and the social sciences, it is so interesting because you understand that really technology is not possible if society do not adhere to technological innovation. So if people, citizens, do not adopt technologies, then technology is totally useless. And power systems are also another crucial point of this marriage, let's say, because we know that power systems are now hosting, at least in Europe, we have these plans, but I know all the world is going in this direction. We have plans of integrated a lot of renewable energy. And the integration and penetration of renewable energy generates weaknesses in the power grid because the generating units have a totally physical different nature from traditional fossil fueled generation systems, So these static systems or systems that are rotating but with different dynamics do interact with the power system. And we And there is no enough technology to support the grid when we have high penetration from renewable energy. So this is why we call people to help for regulation purposes, so to deliver services to the power grid. And again, we need that they do that. Yes. We need them to be committed to the energy transition. So we need them to believe in the value of adopting renewable energy in your country. Of course, I think renewable energy in each country has a different perspective. Yeah. So in Europe, it has a value which is related, for example, to energy security, because we are very much reliant on import of energy sources. We have an import percentage which is around maybe 60%. This is really, really high. Why, for example, in the United States, you have a totally different situation, right? Yes. So here motivation will be different, will be maybe more related to climate change. Yes. Yeah. For example, extreme events are affecting you. Or, for example, you may have an issue of connection to the main grid. And so maybe you can detach microgrids, parts of the power grid, and operate them by yourself. But again, these kind of systems need people to interact efficiently. So this is my journey.
Wonderful. Eleonora, thank you. I think this is really such a nice kind of example of how because you said in high school you studied Latin, right? Kind of social study, and then your training becomes so more focused, and then at UW probably kind of very, very focused, right? And then now you are getting back, as you mentioned, the high school. Exactly. And I think it's such a nice cycle, and also it represents kind of the very the very good consistency of your intellectual curiosity. All right. So speaking of that. Power grid and also energy system, and I think it's really at such a nexus of so many different challenges that we, either a nation or our human society as a whole, we're facing. So, Eleonora, so in your mind, because at this stage, right, you have the freedom to choose any topic. Exactly. You can research into, and you must, I think all of us, we want to identify a topic that we can spend our time and our career to address some of the top challenges that either our nation or our society is facing. So in your view, what do you think as some key challenges that you think is worth your time?
Well, there are many, I should say. Yeah. And also my exposure to policy, the recent exposure to policy, which started in 2020, as you reminded, as I work with the European Commission and the other representatives of the member states to design research calls in Europe, in the largest research program for Europe, which is Horizon Europe. These are 100 billion euros that are to be devoted to research and development in the programming period, which is 21-27. So the challenges that I foresee are many and are related, of course, very much to the European context. So I've been very much attracted by what are the European weaknesses, so to say. So, for example, we are very weak about raw materials, for example. So the provision of raw materials or the identification of renewable energy technologies, or in general, energy transition technologies. So, for example, conversion systems like electrolyzers, fuel cells. So those pieces of the energy systems that interconnect different energy carriers, these technologies can contain critical raw materials in different percentages, right? Yes. Yeah. And so this, for example, going to look, for example, to the perfect combination of technologies that would, for example, be more feasible for our European context. This is an optimization problem that probably is very interesting to carry out, right? And in general, looking at the supply chains is very interesting, I think, now. In these times of crisis, I've seen that it's really, really interesting to look at the bottlenecks to look at what really stops the adoption of some technologies, not only from the human side, as I mentioned before, but also from the possibility to provide in a certain area and at a certain time a given technology. So this, I think, is an interesting challenge. Another important challenge, I'm not really a specialist of that, but I think that people could be very interested to look at in it, is about cybersecurity. I think we have a big challenge about cyber threats coming from abroad to our critical infrastructures. For example, in Europe recently, we have a delegated act on the cybersecurity of electricity flows between the member states. So this means that the European Commission expects that we will have cyber threats on the flows of electricity and calls our transmission system operators, so our grid operators that operate in the high voltage grid, to coordinate, to have some recovery plans that are common, so that we can really react all together in the same way if something occurs. And something has occurred already, because our power plants were designed not to be cyber secure. They were designed maybe 10 or 15 years ago or 20 years ago, when these kind of threats were not appearing. So this changing world really is putting a lot of challenges to us. I made these two examples, one about resources and the other one about cybersecurity, which probably give you the idea of how vast or how large can be the range of options that can be interesting now.
It's so wonderful you mentioned these examples, materials, because, key technologies will be really dependent on, those materials, for example, those rare minerals that people talk about. And also you mentioned this cybersecurity, particularly related to power grid. So I think it's so interesting. And also I think this is going to be a very nice transition to your more specific research. But I feel that that's probably the reason why you are doing this kind of research, because you are looking for some system solutions. Because when you mentioned this kind of the dependency on the rare materials and also technology and also this cybersecurity, I feel on one hand, like when we have because in different places, different regions, they have some resources rich, some resources they're lacking of. So as a result, we want to get all the different places networked. Yes. We want all of them to be connected, networked.
Yes.
So that's a benefit, kind of, so that you can really, have all the different things flowing on the network, including electricity flowing on the network from one place to another place, from the lower price to a higher price places, so that we can, right? But in the meantime, networking increase the vulnerability, particularly in face of, for example, cyber attacks. So that's something. So that's actually lead me to your talk today. Of course, I don't want to reveal too much of that, but you are going to talk about a distributed and a secure architecture. I feel that is going to be really the key to address those things, because to increase the security, not only cyber security, right? While we want to increase the network, but also we want to control the network so that we can maintain a distributed security and the sustainability. But in the meantime, it's so interesting. You get all the keyword, and then because it's a distributed network, and we have all this self-consumption and all these kind of distributed communities. So each of them, they will have certain level of autonomous power. But in the meantime, and even take the European Union as an example, to increase overall security, you do want this distributed community to make some collective decisions. Exactly. So basically, I'm transitioning to some of your research area. So please, let us dive into those areas. So maybe we can. Why distributed?
Distributed because we think that not having a central controller means to eliminate the single point of failure. So if we have the possibility to distribute the functions and really do in a way such that if one of the devices that are part of our structure, of our community, because then we talk about community, energy community, but people are interfaced to the physical grid with a digital device, which is an energy management system.
Yes.
And this may stay in a fuse box and may coordinate the loads or the appliances that are within a house, if I talk only of the electrical environment, right? And this thing will have to coordinate with other devices that are similar. If their work is, so to say, it's indifferent if one of those fall down and the community still is up, then this is a resilience thing, right?
Yes.
Otherwise, if we have one point that controls the others, so elaborates information that the others cannot, this is a single point of failure.
Yes.
So we wanted to create a structure of a community, of an energy community, that was resilient to a possible fall of one of the components of the community. So one of the properties of this solution that I will present today is that even if one of the EMS falls, nothing happens. So there is no central coordination. Okay?
Yes.
And this is one. And the other feature, which is embedded in the title, is that these guys are sharing data, but not information. So meaning that they are sharing consumption data that are hidden somehow.
Yes.
So they do not share their private data.
No.
Okay? And in a way, so that they can still compute their optimum strategy, each of them. So this is, the innovation that we're bringing. We're still working on it, so it's a work in progress. So today I will give the first results of our experiments, but it's a PhD project. So I'm very happy to have this PhD student, and hopefully we will end up with something practical in the lab. We're actually working in parallel, both on the implementation of the embedded systems and on the theoretical architecture. So this is what I will talk about today.
Eleonora, I think this is so fascinating because it feels to me that if this problem can be solved, it's like, you find like a silver bullet. The reason here is that because you mentioned you mentioned data sharing. And of course, that immediately touch upon the business secret or privacy of those things, such that those participants, they might not be willing to share. However, hopefully through your through your architecture, that people will. It's really about mutual value generation for all these participants.
Yeah.
So, do you foresee? So let me ask you probably this: how optimistic do you feel about finding a solution? Because very fundamentally, right? So because even as a very neutral, this like a social planner, decision maker, right? To make the system optimal decision, you really need to know the individual data.
Exactly.
To do that. So, and also the more data you have, the better system optimal decision that you can make. So that way you need to get the data. So that means kind of they need to, at least they can perceive a risk of sacrificing their privacy. And then, so I feel you need a very, impartial, like a broker. So in your architecture design, how do you deal with, these participants, right? You need to know their data. So you say they're going to share the data. Who are they going to share data with, or what are they going to share the data to? So kind of how do you design that part?
Well, they actually will, as I said, they will share the data, not the information content. So this means that they will share their data, but with, so to say, a random value on top. So that in the end of the day, they don't know the complete information. They only know the part of information that is needed for them to carry out the optimization. Yes. This is something that is inspired from cybersecurity, actually, theory. Yes. And this is called secure multi-party computation. So, and secret additive scheme. So we took this idea from that, and we designed this way to interact among the different units. Because in energy communities, and in particular in collective self-consumption, what you want to do is that you want to maximize the minimum between the energy which is injected in the grid and the energy that is consumed. In this way, if you maximize the minimum, this means that it's as if you try to fill the gap. So you try to put together these two curves and you obtain perfect self-consumption, right? Yes. And you do this at the scale of the hour. This is imperfect, actually, from the power system point of view, because you could have 15 minutes in which you absorb a lot of electricity and another 15 minutes in which you produce. So from the congestion point of view, and power systems engineer know this thing, it's a problem, because you have a problem of maybe overload or the other way around. But this is the legislative framework we're working with. So we have this objective of minimizing this difference between these two curves. And so each user actually does not need to know exactly what the others are doing, but they need to know the aggregate behavior. Yes. So if you make up some mechanism for them to know what is the collective behavior of the others, each person can optimize his own strategy. Yes. Right? Yes. So this is the secret. Yes. Yeah. I don't know if I was clear.
Oh, that's very clear. So basically, I think I like that idea. It's basic, collection of private data for public good.
Exactly.
Right. I think it's really
exactly. Yeah. This is the synthesis.
Yes. One thing. And you mentioned kind of even the model, right? Of course, we get into the math, all this optimization. Actually, now it turns out to me that a lot of researchers, they try to, how can I design algorithm to solve this optimal optimization problem? But it turns out that actually the key
is the model.
It's really the model itself, how you formulate. Exactly. So for example, how do you decide on your objective function? Yes. And the constraints. So particularly when you mention it, you want to minimize that gap. So basically you want to minimize the supply and demand, that gap. Exactly. So that ideally the supply will match the demand even on a 15 by 15 minute interval.
Whatever it is.
Right, whatever it is. So with that, because I'm thinking that we know that optimality is good, but a lot of times, optimality is not robust. Yes. It could be very crisp. So which means that, but even a subtle disturbance to the system could mess up the whole system.
And then sometimes you read some papers, they go so into the details. Yeah. But the details are so useless.
Yeah, I agree with you.
You agree with me? So I mean, I know literature is fantastic and you have to be rigorous. This is correct. Yeah. But I think you have to be rigorous when this is required. Yeah. Moreover, companies, industrial systems, they require simple things, not too complex things.
That's right.
Is it right? So probably we have to go for simple things that work well and that are robust, as you said. Robust to variations, to unpredictability that is always behind the corner. So I think this is one very interesting thing to look at. I mean, this is something that I learned, of course, in the last part of my career, I should say. Because first I always was struggling to be very, very precise and very, straight to the point and everything well defined. But then you see that the model is so important, and the model really influences the optimization strategy you're going to use. So the more simple you are, the more robust optimization strategy you get.
Yeah, yeah, totally. It's actually, that's kind of I was going to ask you. So for example, because right, when you set up the model, actually probably after the model is set up and you can try. And I was just wondering, like from a system optimality, and also if you consider also certain level of resilience or robustness. So maybe you could conclude that actually we should not pursue every 15 minute this matching. Instead, on an hourly basis, what should be the a good time interval, right? You run a model that will give you not only say even suboptimal but very robust.
Well, this depends very much on the rampings, I think, of all the devices that are in the power system. So what kind of dynamics really you need in that power system? I think.
The capacity, capability of the technologies.
Yes, what is upside, I think. It's not only a matter of how the community behaves, but how the community behaves in a given electrical context, I think. So in Italy, we have the hourly scale. But hourly scale is considered by the regulating authority too long. We are looking for the 15 minutes actually. So we're going to a little bit tighter time interval. And probably it is because they're reasoning on these kind of things. So probably the 15 minutes will be the ending time frame that we will look at for self-consumption.
Yes.
Which is also the billing time. I mean, we do the bills on the 15 minutes times.
So which means that probably it's kind of some intermediate traders of electricity do the bid, like the bidding cycles is also 15 minutes. I see. Yeah, I think that's very nice. So Eleonora, you mentioned earlier, it's kind of through algorithm and mathematical model, and we have the technique to solve those, but at the end of the day, we hope that we can generate some insights or principles that people can use in making their decision, right? So, so here, right, I think you have two levels. One is this self-consumption, which is kind of these individual players, and then these individual players, they will dance to the rhythm that this collective. Maybe this is a virtual thing, or it could be in the future, it could be an AI thing. Yes. Doing it here, right? So, so what kind of principles do you see in balancing this collective decision making versus this, this distributed responding? Because these responders, they also have certain level of power, right? We want to, because we want to give them flexibility and power. And also, however, this collective decision maker also have. So roughly, do you have a sense, you say, actually, in terms of decision making, in terms of power, they should probably have 50-50%. Or you feel actually, this collective decision maker should have more power, while these individuals, they do have the flexibility, but their role is probably 20%. So do you have a rough, this is probably,
Probably, if I understood well the question you're putting, it is about the principles on which the decision maker, the policy decision maker, or the person who designs the tariff is using, right?
Yes, yes, that's right.
What are the self-interests of the end users? Is it this what you meant?
Yeah, that's what is kind of the roles. For a system, for optimal system, taking power grid, the system you're working on. So basically, I see two types of players. One is all these individuals.
Yes. These energy communities.
Yeah, or self-consumption, right? And then there is this social aware planner. So after the question I'm hinting towards, you see, in the end, it's basically the consumers and the governance. So what should be the power? Actually, this is a bigger question. You can see that in the back in the 1930s, when the country was recession, right? So there's always among economists that are talking about what should be the role of the government versus market. So actually, that's my question. You can see that because here, right, when you have this collective, that's basically governance.
Yes.
While you have this self, that's basically market, right?
Well, it is a very difficult question.
It is.
It is not easy. Well, the regulator for the time being is designing possible business models, but also incentives, right, for certain behaviors. And what we see is
incentives will come from the taxpayers' money.
Yes.
That's the fiscal things will come in.
It is exactly like this. Part of our bills go to the incentive system, right? Mm-hmm. So we take out from our bill and we put it into a collective program that should serve all, right? Because we are incentivating a good behavior, let's say a social behavior of all of us. So what I could see till now is that this kind of programs do work well when the incentive is designed well. I mean, it is worth for the people who should adhere to the program. Mm-hmm. If it is not worth, and that depends on personal income. It depends on the economic
and the market itself.
Yeah, and also on each family's status, right?
Yeah,
because for me, $10 can be a lot or can be very little money.
Right? Yes.
I don't know. That depends on the income.
Yes.
And here also comes the concept of utility, right, in economics. Yes. And so this is why I thought that the game theory framework, and at least looking at this topics of microeconomics was very interesting for me.
Yes.
To gather a little bit of further understanding of what was going on in energy communities. Because in Italy, we have a very advanced model for advanced legal framework. We were maybe one of the first member states starting this model of supporting collective self-consumption across Europe. But, these energy communities really are not starting very well. They're very slow. And I think that it is because the incentive is not well designed for our society. Because in certain part of the country, there is not mutual trust. So people will not put together to create a legal entity. Mm-hmm. So there is a number of issues that the regulator should account for when they design some incentive policy that concern really the local conditions. It is really difficult. It is not easy.
No.
It is not easy because you have to design one policy that goes well for the whole country, but the country is so different.
That's right.
Right?
Yeah. And the countries are so different. And also, these countries, if you talk from a systems point of view, these countries are all legacy systems.
Yeah.
Right? It's not like, Eleonora, when you design this mechanism in the end, you said this is perfect. But then when you think about implementing that, it's not like, you are going to draw a picture from a blank piece of paper.
Yes.
You are facing so many cultural and this legal, institutional legacy systems.
Yeah.
That almost makes our models impossible.
Exactly.
Right. That's a challenge, but also I think the beauty of that. That means that first you come up with a model, assume that we can work with a blank piece of paper that work, and now you make it more complicated to add into things.
Exactly.
Yeah. I think this is so interesting because so look at this, this energy usage or climate change or even food security. These problems, they are different from, say, how Apple decide how many Apple iPhones they're going to produce. Because iPhone, those are the consumption of, like, you buy an iPhone doesn't affect me much. However, like you and I were next door neighbor, like when you using this electricity, and then that will affect me. So it's really, I feel, and there are so many things, environmental governance, energy governance, and even climate governance. They share the same nature like you are addressing now.
Yeah.
So I think it's really I really hope, your work will come out, with those, because that can help contributing to, it's really, I think, the governance. I think it's really about the governance of how we can provide public good, right? In a very, resilient, sustainable, robust way. It's really exciting. So speaking of that, probably both you and I feel that while you are now at this stage, you see these things, you're approaching these things this way, but you probably feel that unfortunately there are not as many people as you would wish that will share your view, share your approach. So that means kind of putting us in the position as educators, we certainly want to train more people that will share your view, kind of not only sharing your view, it's not that we're going to, put our views in other people's eyes or minds, but it's really kind of giving them the approach and basically getting towards education. So Eleonora, how can we train and educate more people that can think, that can solve problems like the way you are doing?
I think the main thing is to be optimistic and to provide young generation a vision towards the future. Because I was reading a strategic document from the European Commission for 25-27, and it was depicting a world of disasters, a lot of threats, behind the corner, and they are there. But if we give our young generation a vision to overcome all these issues and a way to go beyond and improve, I think this will attract more students and will make our society more resilient and also able to overcome the problems that we will have. So I think that the first thing is what you're doing in your system engineering program. So provide a broad view on things, on what is happening to our world, because consciousness is the first thing, but in an optimistic view. So provide visions. So try to see what in the US is going to be done for them, for their future, and tell them how they can contribute to this big picture as individual and as a community. So I think this is very important for us as educators. I hate those persons of our age that are pessimistic. I hate them because I think it's not the right attitude. I mean, we grew up in a world of optimism. We were looking at the future, thinking that everything could only improve, right?
Yeah, we work out.
We could only improve. And why don't we have to give the same picture to our young generations? I think we have this commitment. We have to do that. And I think that systems engineering gives you the possibility to do that. It gives you a wide space to give the big picture.
Yeah, the holistic way to look at it.
The holistic way, yes. And the holistic way gives the hope. Because if you look at one sector, then you maybe can be pessimistic because you look only one piece of the big picture, right? But if you see the big picture, you see the connection of the dots and you see what can be the direction for improvement. This is what I think.
Wow. Eleonora, thank you so much, because I feel that you address, I conduct this system conversation with many people, and when we talk about education, and mainly of course because of the technical background, we dive into, okay, we should have students learning math, we should have students learning this stochastic problem. But I really appreciate you started but not saying those. Actually, I feel because we're talking about education. Education, you hit such a fundamental thing of education. And education is not really just about giving the student techniques.
Yeah.
It's really
it's one part.
Yeah, but it's also really, more importantly, as you say, it's kind of giving people the hope.
The hope. Exactly.
Because I think if they have the hope, and they will self-drive to get these things. Because this reminds me, and But I totally agree with you, and this is so fundamental. And the reason why you see that I'm so excited about what you just said, because I remember, and even you look at the social animals. Human beings are also social animals. The bees, right? Monkeys or dogs, and you observe that actually they are, because when they are feeling secure, they're not aggressive.
Exactly.
It's very easy for them to coexist in peace. But then, as soon as they feel insecure,
yeah, it's true.
And then it's not only actually it's kind of you and me, or it's kind of the bees. 1 second ago versus 1 second now, and even nothing changed. However, if their perceived security, if their perception of security change, and their behavior will change, and then so that could easily lead to wars rather than peace.
Exactly.
That's why I feel what you said is so fundamental. It's really because otherwise, kind of you said some of those documents, the vision of documents, that if they're instilling this kind of sense of stress, that plant the seeds. And even no war now, but that can plant the seed for, by war I mean quote unquote wars, So, and that is only that. So that also means the education goes beyond universities and in the government. Because those documents you are talking about, those are probably from the government, right? Of course, they have the responsibility to protect. Right, but somehow, how do you control? How do you come to the optimism? How do you identify the appropriate amount of insecurity that you need to get to the people, but in the meantime, maintaining this sense of hope? How do you do that? Sorry, I'm throwing these difficult questions.
This is difficult.
Yeah.
Yeah. Well, I think it's correct to be informative, so to tell what are the challenges, but at the same time to give the tools to cope with the challenges. So this is why the technical aspect is so important, and being rigorous with the technical aspect. So what probably other colleagues have said in the conversations were also correct things. I mean, students have to be strong in maths, in physics, in information technology, and if they study machine learning, whatever. But so they have the tools, and they have to connect these tools to the world they are living in. So these things have to be related to the applications that will bring improvement to the society. So this is, I think, how we provide a vision of recovery and of optimism. This is what I think.
Beautiful. I really like it. Kind of, based on, I'm trying to rephrase. It seems to me you are saying, translate political. It could be different. Translate political insecurity into rational hope.
Yeah, exactly.
Right. I think it's kind of, because that way, rational hope actually will overcome all those other challenges.
Exactly.
Wonderful. It's such a pleasure to talk to you. I think our time is up, and we will.